Hey guys, what's up? In this section, we're going to look at the idea of limit for functions of two variables. Let me start off by recalling the idea of limit for single variable function. Suppose we have a single variable function f of x. We say that the limit of this function f is equal to the real number L as x approaches a if x gets closer and closer but not equal to a. The function f of x gets closer and closer to L. As you might have noticed, this is not a rigorous definition of a limit. However, it does give us a good intuition about what limit is. So we are going to extend this informal description of limit to functions of two variables. Alright, suppose we have a function f of two variables, x and y. We say that the limit of this function f is equal to the real number L as xy approaches the fixed point AB, provided as xy gets closer and closer but not equal to the fixed point AB, the function f gets closer and closer to L. Before we look at this informal description of limits in a more rigorous manner, let's look at what we mean by xy getting closer to a point AB. Well, as it turns out, for functions of two variables, any point xy in the domain can get close to a point AB in infinitely many directions. As you can see in the figure here, there are four different paths along which a general point xy can approach a particular point AB in the domain. So in general, there are infinitely many such paths that we can use to approach a particular point. Now, this is different from the case when we consider a single variable function f of x, where the point A is a point on the real line and a general point x can approach a particular fixed point only in two different directions, either from the right or from the left. So this is the case when we consider the limit of a single variable function f of x. However, for functions of two variables, x and y, any point AB in the domain can be approached in infinitely many directions. Here's one example of a two variable function given by x squared minus y squared. As you might have recognized, this is an example of a hyperbolic paraboloid. So let's go and fix a point in the domain and look at the limits of this function at that particular point. Suppose we choose the point minus 2, 0 in the domain of our function f. The limit of this function at this particular point turns out to be 4. For now, let's not worry about how this limit came about. Instead, we're going to use this as given. Let's say now we take a path along which the point xy is approaching the point minus 2, 0. There will be a corresponding path on the surface which is vertically above this path. Let's say given by this curve here on the surface. For example, for the point xy on the path below, there will be a point above, vertically above this point xy, and that coordinate is given by xy comma f of xy, because that is the surface for our function. So the z coordinate is the value of our function at that point. Now what happens is that as xy gets closer and closer to minus 2, 0, the z coordinate of this point on the surface will get closer and closer to 4. In this case, this path on the surface vertically above the path we have in the domain will get closer and closer to a particular point above minus 2, 0, where the z coordinate is given by 4. This is true for any path that we pick as long as it approaches minus 2, 0. So let's say we have another one here that goes this way, then there will be a corresponding path on the surface that eventually gets closer and closer to this point given by the limit. Alright, from the previous example, we have a visualization of a limit, as it were. Now let's see how we can make this intuition more rigorous. Well, it all came down to this concept of closeness, which mathematically speaking is equivalent to that of distance, meaning two objects are close to each other if and only if their distance is small. Now, in the definition of limit, the points x, y, and ab are points that lie on two-dimensional plane, so that distance is given by the expression square root of x minus a squared plus y minus b squared. Now, for these points to be close to each other, we want the distance to be made small, let's say strictly less than some positive real number delta. Also, since xy is not equals to ab, this distance cannot be 0, hence it must always be strictly more than 0. On the other hand, for the function f to be close to L, we want their distance to be small as well, since both the value of a function and L are real numbers, their distance is just the absolute value of the difference. So we want this distance to be strictly less than some positive real number, let's say epsilon. And here comes the big idea of limit. We want the value of our function to be as close as we wish to the limit L. In other words, we want this distance between f and L to be arbitrarily small, meaning we must be able to choose the epsilon as small as we wish. So to write this down properly, for any epsilon that we choose, we want to be able to find a delta, or there must exist a delta which is positive as well, so that this implication holds, meaning when xy is sufficiently close to ab, then our function is that close to L. Well, how close? Epsilon close, for any epsilon. So essentially this is the formal definition of limit. Okay, we have written down here the formal definition of limit for functions of two variables. So basically, if f is a function of two variables whose domain D contains all the points arbitrarily close to the point AB, we say that the limit of this function as xy approaches AB is the real number L, denoted by this equation, provided for any positive epsilon there exists a number delta which is positive, such that the distance between f and L is strictly less than epsilon whenever the distance between xy and ab is between 0 and delta. Perhaps an important point to note here is that the function f is not required to be defined at the limit point ab for the limit to exist. In other words, it is possible that a function is not defined at ab, but the limit exists at ab. Also, it can be proved that if the function f has a limit at a point ab, then this limit L must be unique, and this limit is also independent of the choice of path approaching ab. Alright, questions about limits usually fall into two types. Either you're asked to show that the limit f exists at a given point ab, or you're asked to show that the limit does not exist at the given point. As it turns out, the methods used to solve these problems are different. Let us first turn to the question of how to show the limit does not exist at a given point AB, let's say. Well, this is based on the observation that if limit does exist at AB, then the limit along every path passing through AB must be the same. So in practice, if we suspect that the limit does not exist, then it is enough for us to check that the limit along certain paths, in fact 2 will be enough, and show that they are different. Please note that these paths that we choose must pass through the point AB. So formally, this is what the approach says. Suppose the function f approaches a limit L1 as xy approaches AB along path P1, and the function f approaches another limit L2 as xy approaches AB along another path P2, and suppose that L1 and L2 are different, then the limit of this function does not exist. In other words, the function does not have limit at this point AB. Alright, let's see one example. Here we want to show that the following limit does not exist. The function here is given by y over x plus y minus 1. That is our function. And the point in the domain which we are interested in is the point 1, 0. How do we know that the limit does not exist at this point 1, 0? Well, we're going to find two paths along which we'll get different limits. Okay, the first path that I'm going to choose that passes through the point 1, 0 is going to be the x-axis. Right, so this is the path P1 that I'm going to choose, and I'm going to compute the limit of my function along P1 as xy approaches the point 1, 0. So let's see what happens if we compute the limit along P1. Well, the expression for our function can be simplified in this case, since y is always 0 on the path P1. Well, this is not the case in general. If we have points which is off the x-axis, then it is not necessary that y is always 0. However, on the x-axis, which is given by the equation y equals 0, any point xy on P1 will have 0 in the y coordinate. Therefore, when xy approaches 1, 0 on P1, we can always substitute y by 0. Therefore, the limit now becomes 0, the limit of 0 over x plus 0 minus 1. And since y is always 0, then we are left with x approaching 1. In other words, we have reduced the limit of a two-variable functions into a limit of a single variable function of x only. But now the function here is 0 over x plus 0 minus 1, which is just 0. Well, notice that the denominator is never 0 because x is never 1. X is only approaching 1. So x minus 1 is never 0. So 0 over something which is not 0 will always be 0. Therefore, now the limit is limit of 0 as x approaches 1. Well, this is just 0 since 0 is independent of x anyway. Therefore, the limit along P1 is 0. Next, we're going to choose a different path, and hopefully it will give us a different limit. Now, the path that I'm going to choose is the vertical path passing through 1, 0. So, there you go. This is the vertical path, which I will call P2, and it passes through 1, 0. Now, because this is a vertical path, it can be easily described by the equation x equals 1. This is because any point on this path will have 1 in the x coordinate. Right, so let's compute the limit of our function along P2. Well, this time the expression of our function can be simplified by substituting x with 1. Because along P2, all our points xy will have 1 in the x coordinate. So this will simplify to y over 1 plus y minus 1. Now, since x is always 1, we are left with y approaching 0. And finally, we have the limit y approaching 0 of the function y over y. Well, we need to simplify this function first before we compute the limit. But after simplification, this is just a constant 1 which is independent of y anyway. Therefore, the limit of a constant 1 is always 1. Okay, so we have arrived at the limit which is different from the one we have previously. Therefore, we have found two paths, P1 and P2 in particular, along which our function has different limits at the point 1, 0. Therefore, there could be no limit in the first place. In other words, the function actually does not have any limit at the point 1, 0. In this example, we are going to show that the following limit of the function xy over x squared plus y squared does not exist at the point 0, 0, which is the origin. As usual, we are going to find two paths along which we'll have different limits. Alright, there seem to be two obvious paths that we can choose to compute the limit. They are the x-axis and the y-axis, since both of them pass through the origin. So let's suppose I take the x-axis to compute a limit as the point approaches the origin along the x-axis. Let me call this path P1, and we know that this is given by the equation y equals 0, since any point on this line will have 0 in the y-coordinate. Right, let's compute the limit of our function along P1. Well, in this case, we can always substitute y equals 0 into the expression for a function, and hence this limit can be reduced by writing as the limit of the function x times 0, which is 0, over the denominator, which is now x squared, since y is always 0. This expression is well defined because x is approaching 0 but is never 0. Hence, x squared is some positive number and 0 over x squared is always 0. Therefore, the limit of our function along P1 at the origin is 0. Notice that if we were to choose the y-axis as our path, the limit along the y-axis at this point origin will also be 0 by a similar argument. So I'm not going to give the details here since it's very similar to the one we have here. Instead, I'm going to find another path that hopefully gives us a different limit, or limit different from 0. Okay, the path that I'm going to choose now is the path y equals x. This is a straight line passing through the origin. So let's see what happened to the function along this path as we get closer and closer to the origin. Let me call this path P2 now. So along P2, the limit of our function xy over x squared plus y squared as xy approaches the origin become the limit of, well, since y equals x, on P2 we can choose to substitute y by x. In this case, the numerator will become x squared and the denominator becomes x squared plus x squared, which is 2x squared. So instead of having xy approaching the origin, we can just say that x alone is approaching to 0 because y is now x. Simplifying the function, we'll have limit of half. Since x squared cancel out, we have the limit of half as x tends to 0, and of course this is always half. Hence the limit along P2 of the function as xy tends to the origin is half. Now this is different from the one we have previously along path P1. Hence the conclusion is the function xy over x squared plus y squared does not have limit at the origin.